Number 52 in chapter 18 looks at an actual line representation for a cell and asks us to do a number of things. First, to sketch the voltaic cell, then to write a balanced reaction, and then calculate the actual cell potential. So our cell involves our anode, which is manganese, going to manganese plus 2, and then we have a salt bridge, and we have ClO2 minus, that's aqueous, Cl2, that's gaseous, that's uncharged, and then platinum as our cathode. So we have our cathode on the right, we have our anode on the left. And then remember, our salt bridge is right in the middle. So if we were to sketch this, we would have, our two beakers, each with a solution in it. The case of the anode's pretty simple. We're just going to have a strip of manganese, that's a solid, and that's the actual anode, and then we're going to have manganese plus 2 in solution. And so electrons are going to flow from that oxidation. Right, we need to have our salt bridge connecting the two solutions. And remember, that's a high electrolyte. We then can pass this through an actual voltometer, and then we have to bring it down to our other solution. And so our other electrode is the platinum. And this one is kind of interesting because you'd have to have a, let's make my beaker a little bit bigger here. You'd have to have a container that's actually in here that's allowing ClO2 gas to come in and react to make ClO2 minus, right? Because if we're looking at our processes that occur, the manganese is going to be oxidized, so it's going to plus 2, but the chlorine is actually being reduced, right? And we can get that from the half reaction. So what they're trying to show here is that you're going to pump in gas, and then some of that is going to come into solution, get reduced, and then be turned into our ClO2 minus. And so then this is the cathode. So that would be our, drawing or cartoon representation of the line diagram representation of a cell that we have above. So that's the first part. The second part is then asking us to determine the overall balanced equation. And so if we look at our two processes, right, in order to get the overall balanced equilibrium reaction, we have to balance each one of our half reactions. So this is the anode process where we're having the oxidation occur. And so we have the manganese going to manganese plus 2, and we have 2 electrons being given off. And then the other process would be the Cl2 as a gas going to ClO2 minus, that's aqueous. Our chlorines are balanced, our oxygens are balanced. So basically we're balanced by atoms, we just need to add electrons. And so we're going here from a plus 4 to a plus 3 for the chlorine oxidation number. So we have to add 1 electron to that side. Now that we know our electron count, right, we're going to cross multiply our oxidation and reduction by the number of electrons respectively so that those are equal, and then we add up the entire process. And so if we add up those two reactions, we would get 2 electrons plus 2 ClO2 as a gas plus manganese as a solid is in redox equilibria with our 2 ClO2 anions that are aqueous plus our manganese plus 2 that's also aqueous plus our 2 electrons. These guys should cancel out, which they do. And so if I just get rid of them, we have now our overall balanced reaction. The next part is actually asking us to solve for the cell potential. And remember, that cell potential is going to be equal to the potential for the reduction minus the potential for oxidation. So we need to look up these two reactions. We are not going to multiply them. We already did that for the balance process. We're just going to go to the table and look these values up. For our oxidation, we get a value of 1.18 volts for its reduction potential, and for the reduction we get 0.95 volts. And so we just want to plug those values in. Our reduction is 0.95 minus our oxidation, which is our negative 1.18 volts. So those signs get changed. And then our cell potential for the reaction is determined to be 2.13 volts. That is number 52 in chapter 18.